have corrosion when we have an acid. We have corrosion when we have a base. But typically we see corrosion when we have oxygen in a metal. Corrosion is spontaneous, okay, which means that it's going to happen. It doesn't require any energy input. So the oxidizing agent is always going to be higher than the reducing agent. So lots of metals are strong reducing agent and spontaneously react with oxygen, because where do we find oxygen on the tables?
Isn't it with water?
Yeah.
Hydrogen?
So we can see it depending if it's we see it up at plus 1.23. Okay? So here's what it looks like when we have iron rusting in terms of electrochemistry. So electrons leave the anode, the iron will break down. So it's telling us this. Blue. So first thing to do, list all your species present. So we're going to have iron. Iron's going to break down into something. We're going to have oxygen. And typically we have water. That's what we're going to be seeing. We know that at the anode we have which? Oxidation or reduction?
Oxidation.
So loss of electrons is electron, which is our reducing agent. Our cathode is our gain of electrons, which is our oxidizing agent. So if the electrons are leaving the anode, the iron will break down and rust. That means that this is going to be our strong reducing agent. And these two components here are going to be our oxidizing agents. So let's look at the oxidation reaction. So when we look, we see iron. Oh, that's not what I want. See iron. So then at the reduction, half reaction, which is our cathode, we're going to see oxygen. Okay. The reason we're picking this one and not the one at 1.23 is because we need the oxygen and the water at the same, together in the same line. When we look at 1.23, we see that oxygen and water are on opposite sides. So we need to be able to balance these, so we're going to multiply this one here by 2. That's our overall reaction. So because what do we get here? We end up with iron oxide, or iron hydroxide. Okay?
So that's like the last step, is you combine any...
Yeah, we have 2 and 4, so we would end up with 2 molecules of that. You don't combine them, I'm just showing you that this is where the rust is coming from.
Oh, okay.
Okay? So your iron solids break down into iron ions. It's said to be rusting. Okay? So we can prevent corrosion by two ways. And this is a very good sales tactic for the automobile industry. You can apply a protective coating. You can get that undercoating, that clear undercoat on your vehicle to help protect against rust from the salt, especially in northern Alberta where we love to apply salt to the roads. Okay? So it prevents air and water from actually reaching the surface of the metal, and it's only effective if the entire metal surface is covered. So what happens is they put your vehicle, I'm assuming, I don't actually know, correct me if I'm wrong, but they'll put your vehicle up on a hoist and they'll spray the undercoating. So which side of the undercarriage are they getting? Just the bottom half, right? But that spray is going up and it's going to get trapped on top of your undercarriage. So unless everything is completely covered, you can't fully protect your engine. So that's why I say it's an additional couple $1,000s onto your, when you buy your vehicle. You have to weigh, is it really worth it or not? Okay? Another way is to use cathode protection. So cathode protection involves using a more reactive metal, so a stronger reducing agent, to the iron object. The more reactive will act as an anode and will slowly corrode and break down due to the oxidation reaction. So what happens is you're creating a sacrificial electrode. So it's going to break that electrode down before it breaks down the iron. Okay? Unlike protective coating, the metal in a cathodic protection doesn't need to cover the entire surface. You just need to replace it. I don't really know where you would use this. I'm thinking it's in industrial processes.
I think so.
Yeah.
Why doesn't this one need to cover the entire surface?
Why doesn't it need to? Because you're going to put, so when we have our beaker, right? We have our beaker like this. And if this is our anode, this is going to break down and this is going to build up. What happens is they would put another more reactive anode in there, so that one will break down first before the iron one breaks down.
Oh.
So that's why I'm thinking we see it in industrial processes before we see it in everyday life
I
processes.
think it's not like you could just cover something with more reactive metal and then it would react well.
And you don't know how you would.
Yeah,
you would have, you would have to build it that way, right? It's not like you could just spray on another metal. So the protective coating is cheaper in that relation, but you have to cover everything. So it's a bit of a trade-off. Okay? So I just set my notes down somewhere. And that's it. So there's textbook questions at the bottom of this one, and it's going to have you looking at different cell potentials to see which one works. Okay?